Hello guys, welcome to today's physics lesson. We are going to talk today about acceleration, so I'm super excited about that. First of all, I want you to know I've started saying mucho to my Spanish-speaking friends. It means a lot to them. Really, it means a lot. Okay, let's get into acceleration before you guys groan and turn this thing off. Sometimes, my genius, it's almost frightening. The reason I put that guy on there is because we hear about acceleration a lot. And if you watch that show, then you hear this term a lot. And so we're going to learn what it means. Basically, I'm just going to tell you up front that it means how much the velocity changes over time. So acceleration is velocity over time. Okay, let's look at some examples of this. Here are two examples of cars. We have the Corvette right here, the yellow one, and the Sonic right here, this red one. Now, I think you can tell by looking at them which one has more acceleration. But if you look at these velocity vectors, you can also tell which one accelerates faster. So right here at 0 time, this dot is 1 second later, 2 seconds later, 3 seconds later, and the velocity vector is showing the direction, as you can see, to the right or east, but it's also the magnitude of the arrow is showing the amount that the velocity changes. So the longer arrow means there's a larger velocity. So every second, the Sonic has a bigger velocity, and same with the Corvette. But as you can see, the Corvette, if we use our previous definition, acceleration is change in velocity over time. The Corvette is changing its velocity more every second. So it's going to have more acceleration. And that's probably going to be the funner one to drive. Here I'm going to remind you of a previous definition, which is velocity. Velocity is how much the position changes per unit of time. So when we wanted to measure changes in position, this ratio, or the rate of change of position, was useful. Rate of change of position is velocity. And remember that you can have a rate of change of position or a velocity time graph that looks something like this. So this is time, this is velocity, and the velocity might look like this. Now, when we talk about acceleration, you're going to notice that acceleration is the change in velocity over change in time. A change in velocity is going to be how much does it change up and down, maybe like that. A change in time is going to be how much does it change on the x-axis, maybe like that. So from here you can tell that acceleration is actually going to be the slope of the velocity time graph, which is so cool. Remember how velocity was the slope of a position time graph? So now it makes sense that acceleration is the slope of a velocity time graph, because if we look at this equation, then this is the change in the y-axis, or the up and down, and this denominator is the change in the x-axis. You guys have probably got this down, right? So to summarize the two things that you need to know that are important about acceleration, this is the first one. The change in velocity over time is the rate of change of velocity. This is the equation for acceleration. The other thing is that the change in velocity over time is actually the slope of a velocity time graph. Don't get it mixed up with the slope of a position time graph, because that's actually velocity. You're keeping all of this straight, right? Woo, let's ease that tentacle off the acceleration, huh? So this is the important equation that you need to memorize and that you need to have dripping off your tongues. Acceleration is the change in velocity over change in time. Now let's talk about units here for a second, because this can be a little bit confusing. The units for velocity, if you're talking about the standard units, are meters per second. The units for time are second. So it's kind of a weird unit where you have meters per second on the top and then seconds again on the bottom. So it's actually meters per second That's how some people say it. Or it's actually the same as multiplying it by 1 over seconds. So that's the same as meters per second squared. That's the other way that you can define the units for acceleration, meters per second squared. But there's 2 seconds on the bottom. And kind of think about what this is saying. To me, it makes more sense conceptually to think about it as meters per second per second. That means that the velocity is changing, maybe 2 meters per second, every second. I know that makes you want to take a nap, right? Let's look at an example. Animal acceleration. So, lions are capable of very rapid starts from rest. So think about that, what they're telling you there. The velocity is going to start at 0. A lion can sustain an acceleration of 9.5 meters per second squared. So let's think about what that means for a second. At 0 time, the lion is going 0 meters per second. At 1 second, the lion is already going 9.5 meters per second. And it's going to increase by 9.5 meters per second every additional second. So in 2 seconds, it's going to be going twice this, which is, 19 meters per second? So the question here is, how much time does it take a lion to go from rest to a typical runner's top speed of 10 miles per hour? Whew, okay, so 10 miles per hour is a totally different unit. So the first thing that I'm going to do to answer this question is let's get this in standard international SI units. Now you don't have to remember this unit conversion. This is one of those things you can keep in your reference page. But here's how you convert the units. I'm starting out with 10 miles an hour here. Now I do my typical little boxy thing there. And I know that 1 mile per hour is the same as 0.447 meters per second. So it's totally fine for me to multiply 10 miles per hour by this, because if this is the equivalent of this, I'm basically just multiplying by 1. It's kind of like multiplying by 2 over 2 or 3 over 3. That's the same as multiplying by 1, and when you multiply by 1, you're not changing the quantity, you're just changing the units, and that's totally fine. So 1 mile per hour is the same as 0.447 meters per second. So if I do the math on that, 10 times this number is just going to mean that I move the decimal over, so I already know it's going to be 4.47. Now, what are my units here? I have miles per hour on the top here. That cancels out with this miles per hour. So the units that I have left are meters per second. 4.47 meters per second. Then I'm going to also take into account significant figures. There's only 2 significant figures in the number 10. So I'm going to erase that and change it to 4.5. So it's 2 significant figures, 4.5 meters per second. So now the only thing I've done here, I haven't answered the question. I've just changed 10 miles an hour to 4.5 meters per second. And now they want to know how much time does it take a lion to go from rest to 4.5 meters per second. Now, if I look at what I drew up here, I know that in 1 second, the lion is already going 9.5 meters per second. So the time it takes to reach this is going to be less than 1 second. And if I get an answer that is less than 1 second, then that answer is likely to be right and it's going to make sense. So let's set that aside. What's my formula for acceleration? And I know that its acceleration is change in velocity over change in time. In this question, they have given us the velocity they want. So they've given us this. They want to know what's the time it takes to go from 0 to 4.5 meters per second. So that's the change in velocity, 0 to 4.5, which is just going to be 4.5, right? Because velocity final minus velocity initial is going to be 4.5 minus 0 because we're starting out at 0. The acceleration is something that they told us. Let's look here. An acceleration is 9.5 meters per second squared. And they're asking for a time. The question is how much time? So let's rearrange this equation and solve it for change in time. Change in time is equal to change in velocity over acceleration. How did I get that? Easy peasy. I'm going to set that to the side. I'm going to multiply both sides of this equation by change in time. This cancels out, so I can just erase that. Then I divide both sides of the equation by acceleration. This cancels out, so I can just erase that. And there you go. So let's plug in the numbers and solve this puppy. Change in velocity is going to be 4.5 meters per second, and the acceleration that they gave us is 9.5 meters per second. And because that's a fraction over a fraction, if you remember those complicated algebra problems you did, this is the same as putting a second on top. Text me if you don't know how that works. Now, look at the units that cancel out. This cancels with this. And let's just do the math. 4.5 divided by 9.5 is 0.47, and the units are seconds. And then we go back and assess our answer. It's going to only take a half a second, about a half a second, for the line to go from 0 to 4.5 meters per second. And that makes sense with the amount of acceleration. The moral of this story, I think, is don't try and run from a lion, because if you're a runner and your top speed is 10 miles an hour, it's going to catch you in less than half a second. I guess you won't be terrified for very long. Good lesson learned. You never know the things that physics can teach you, right? One more little reminder here. Let's take a look at the Sonic and the Corvette one more time. This is a table showing the velocity data for the Sonic and the Corvette. So these velocities are for the Sonic. These velocities are for the Corvette. Time is here. So at 0 seconds, they both start at 0. Makes sense. In 1 second, the velocity of the Sonic is 3 meters per second. The Corvette is 7.5 meters per second. And by the time you get to 4 seconds, the Corvette's way ahead, obviously. Now, if you plot that on a velocity time graph, velocity is here, time is here. The Sonic shows this line, which makes sense. At 1 second, you're just plotting the different velocities that are shown on that table. You can do the same for the Corvette. Just plot the velocity at 1 second, 2 seconds, 3 seconds, 4 seconds. Obviously, the Corvette's going to have higher velocities. And so the acceleration, which you recall is the slope of the line, is steeper. Remember, acceleration is change in velocity over change in time. Change in velocity is this up and down. Change in time is this change in the x-axis. So a steeper line means more acceleration. Remember that an object's acceleration is the slope of its velocity time graph. What if the velocity time graph looks like this? Here's velocity, here's time. What's happening to the acceleration during this initial segment? What's happening to the acceleration here? And what about here? So in this part, I just said that the steeper, the more acceleration. So we can see that the acceleration is high during that initial phase. And if we plot the acceleration versus time, you can see that the acceleration is high. At this point of the graph, the velocity is not changing. the velocity, whatever it is, stays the same over this period of time. If the velocity is staying the same, there's no acceleration. Acceleration is 0. Look at this part of the graph. The velocity is going from whatever it is here back down to 0. This means it's decelerating. If it's decelerating, let's assume it's decelerating and going to the right, then the acceleration is negative. This tells us one more thing that's important about acceleration, that acceleration is a vector, just like velocity. In the next lesson, we're going to talk about what that means for the sign of the acceleration, because it's not quite as intuitive as it might seem. But we'll get to that fun next time. That's it. Nothing else for today. Have a great day. Bye.